Okay. So after this, there are 2 lectures next week. There's no lecture on Good Friday, so next Wednesday is the last lecture. The assignments are due to, well, 3 weeks from today, so everything has to be handed in within 3 weeks from today. Want to start today and next lecture, at least, I'll be talking about type 2 matrices. The simplest example is unitary matrices with all entries at the same absolute value. We're going to see there's a number of reasons looking at them. The immediate one is there's a connection. We can use them to construct quantum permutations. But they're also an interesting topic. They turn up in lots of different parts of combinatorics in one form or another. So so this is in some sense also part of motivation that a clique. So this is the this is the graph for the unit vectors in R to the D with all entries having the same absolute value. So the flat unit vectors in R to the D. And so a clique in this graph is actually a flat D by D matrix. And so it's a D by D unitary matrix. And we use them to construct homomorphisms between various graphs. So they turn up in various places that we're using. Now, normally, often in the literature, when people are working with it, they just take one particular flat unitary matrix, which you get from the Van der Waals matrix, which I'll talk about later. But each flat unitary matrix gives you a homomorphism, and they turn up in various places. And so we're going to look at a somewhat more general version. Now, one reason to look at the more general version is that the more general version is also connected with knot theory. In particular, under some very special conditions, you could construct interesting invariants of links using type 2 matrices. Okay, and so that's another reason why people are interested in them. So time for definition. If W is I don't require to square an MBN matrix over C with no 0 entries, we define the Scher inverse just to be the matrix you get by inverting the entry of each element. So this is the inverse that the undergraduate students really wanted in matrix theory. Okay, and we call it the Scher inverse of W. Okay, now in practice, I will be taking Scher inverses of vectors and things like that. Okay, but outside that context, we're either doing the vectors or with square matrices as a rule. So so to find the Scher inverse, so an n by n matrix over C is a type 2 matrix if the product of W with the transpose of Scher inverse is n times the identity. Now, let me just do a quick comment. If I have a type 2 matrix with entries W1, W2, and I take the inverse transpose, I'm going to have this W, this is W inverse transpose. You can see that when I take the product W times W inverse transpose, the one entry is going to be N. Okay, so you have no choice about that N there, it's forced on you. Okay, so the only thing that's special, the thing that's special is that, you will see later on that any flat unitary satisfies this, modulo scaling, which we don't care about. So if we have a type 2 matrix, it's guaranteed to be invertible, and its inverse is just the transpose of the Scher inverse. So it's not quite what the undergraduate wants. To get the inverse, you have to take a transpose, but this is linear algebra. There's always a transpose hiding somewhere. I'll show you for that. So this is the definition. So the type 2 matrix is invertible. The inverse can be written as the transpose of the Scher inverse. Okay, so examples. Well, I suppose the 1 by 1 matrix, you could do 1 as an example, but let's be not quite that trivial. So this 2 by 2 matrix is a type 2 matrix. You can go and check the definition, or you can sort of cross your finger and wait till we prove that flat unitary matrices are type 2. Although I might leave that as next slide. So this is actually a Hadamard matrix. And any Hadamard matrix is going to be a type 2 matrix. It's flat and orthogonal. Okay, so that's unitary, so we're all right. Just to make life a little more interesting, if you pick as a generalized, I picked a cube root of 1, not the identity, not equal to 1, and write down this matrix. That's a type 2 matrix. Okay. So far, this is a flat type 2 matrix. I better give you an example. It's not flat. So this guy here is a 4x4 matrix, and the bottom 2x2, that bottom square there has got an entry T, which I require it not to be 0. But if I take T to be any non-zero complex number, this is a type 2 matrix. And so this, this tells us that type 2 matrices don't have to be flat, although the ones that we concern ourselves most will be. As I've mentioned a couple of times already, any flat unitary matrix is up to scaling a type 2 matrix. Now, so if unitary matrix U, you get UU star equals the identity, and we want U times U sure inverse transpose to be N times the identity. So now, if you've got a complex matrix with a flat complex matrix, then the complex conjugate is the sure inverse. Okay, and so because of that, well, you have the following result. I've managed to fit it all here. So for any complex square matrix, the following equivalent: W is type 2. The scaled matrix n to the minus 1/2 W is unitary, and the matrix is flat. Actually, I think I will be leaving this as an exercise. So for our purposes, the flat unitaries will be the most important. But as I said, the general case turns up with connection to problems in knot theory and various problems in design theory and geometry. So they turn up all over the place. What did I want to say about that? Now, at some point, someone's going to ask me about why this is type 2. And I'll forestall one question by saying a type 1 matrix is a matrix with constant row and column sum. And if you ask me, I might tell you what a type 3 is, but you'd be better off if you don't ask at this point. I'll come back to that point. The terms come from knot theory, where there are Reidemeister moves on knots for type 1, 2, and 3. And so the 1, 2, and 3 here correspond to these knot theory operations. So as I said before, any Hadamard matrix is type 2 and real. We can also get flat unitary matrix from continuous quantum walks. So I'm just going to review some of the material. So we have a continuous quantum walk starting at a state D. Then we say we have local uniform mixing at time t if the state at time t has got constant diagonal. Now that means when you measure in the standard basis that you get your output is an index from 1 to n, and all indices are equally likely. Okay, so that would be local uniform mixing at time t starting from state D. Now we're not going to start from such general states. We're going to start from what I would call vertex states. Okay, so we're interested in the case where the initial state is a vertex state and denoted either by D sub A or E sub A transpose. So this is a diagonal matrix with one diagonal entry equal to 1 and everything else equal to 0. Okay, so that's the so in the context of mixing, it's almost invariably assume you're starting on a vertex state. Okay, although you can define it more generally. Okay, so the point then is if we look at what happens at time t, we have this. And what the point of this little calculation is that the left-hand side is the outer product of this vector with itself. Now this is just the A column review of t. Okay, so at time t, you're looking at the outer product of this vector with itself, and you want that to have constant diagonal if you're uniform mixing. Now, if that has constant diagonal, that implies that UT over EVA is flat. And I'll let you think about that. It's not difficult and it's useful. Okay, so the point is that so constant diagonal at time t is equivalent to this vector being flat, because the diagonal entries are just the squares of the absolute values of the entries of UTEA. If they're all equal, the vector is flat. Okay, and so that's how we can. And so starting at a vertex state, we can say that you've got local uniform mixing at time t if this vector is flat. Okay, and so you don't have to talk about density matrices if you don't want to. Now the jargon is we have. I probably should highlight this a bit. colors. We have, although I defined it before, but it's so long ago. We have uniform mixing at time t if u of t itself is flat. Okay, so the point is, if we start to get uniform mixing starting from vertex A, we want the A column of u of t to flat. What we'd like to have is we want to get uniform mixing at time t, no matter which vertex state we started at, which is a strong assumption. Okay, but that is equivalent to assuming that at time t, the unitary matrix is flat. So, so we get uniform mixing starting from any vertex at time t, if and only if the transition matrix u of t is flat at time t. Okay. Now, there will be flat unitary matrices which are not arising from quantum walks, because if you're getting a unitary matrix from a quantum walk, it's x with ita for some graph A. And there'll be flat unitary matrices which don't arise in that way, but still there are some that do. And the first convenient example is if you look at the d cube at time pi on 4, then you get uniform mixing. And it wouldn't be a bad exercise to actually work out what the matrix is, but I won't go into that right now. So my point is that if I'm looking for uniform mixing on continuous walks, in this sense here, then we're constructing flat unitary matrices. Okay. One way which the condition that you flatten no matter which vertex you start at, you'll get that for free if the graph is vertex transitive. So for the d cube, to prove that I get uniform mixing in the sense I just defined, I just have to show that for one vertex, I'll get uniform mixing at time t. Okay, so this is basically giving you some idea about where these things can, flat unitaries turn up. And so now I want to go on and address some questions about the properties of these type 2 matrices. And okay, most of it's fairly straightforward. If the matrix is type 2, so is its transpose. Okay, you just take, so that's not a problem. The Kronecker product of type 2 matrices is also type 2. And again, it's worth thinking about it a little bit, but it's okay. So we can, and so once I write down one, well, we have all the head-number matrices to start, but the moment you have a flat unitary, then the Kronecker powers of that will give you more flat unitaries. So the long and the short is type 2 matrices are in some sense relatively common. Okay, if you're aware of them, then you'll find it in various places. Now, the next thing, of course, is with matrices like this, there's questions about when two things are equivalent. And so what operations are we going to allow? Well, if I permute the rows or permute the columns for type 2 matrix, it's still type 2. If I multiply rows or columns by non-zero scalars, it's still type 2. Now, the product of a diagonal matrix with non-zero entries and a permutation matrix is sometimes called a monomial matrix. And so if I want to use jargon, I can say that a matrix, if W is type 2 and M1 and M2 are monomial matrices, then M1W, M2 is a type 2 matrix. But so if you permute and scale the rows and permute and scale the columns, you get a matrix which you can take to be equivalent. So this means you can always arrange for the entries in the first row or the entries in the first column to be all equal and all equal to 1 if you want. So you can normalize things to an extent. The convention is that although the transpose of the type 2 matrix is a type 2 matrix, it's not defined to be equivalent. Now, I think this is it's the right thing. It's the usual thing in this sort of area. It's still just a convention. Okay, as it happens, so we define them to be equivalent if you can get from one to the other by permuting and scaling rows and columns. The matrix and its transpose are not, in general, considered to be equivalent. They may be equivalent, they may not be. Okay, so it's just, I mean, you can ask why. All I can say it's a convention, and I think it causes serial problems. It's nice to consider the transpose separately in some sense. And I already mentioned the Kronecker product of two type 2 matrices is type 2, so that gives you a larger supply. Okay, so any questions at this point? Because now we're getting down to the dirtier stuff. I'm going to construct an algebra associated, actually a pair of algebras associated to each type 2 matrix. Okay, so first the notation. I'm going to use W subscript I over J to denote the ratio of the basically the ith column and the jth column of W. So it's the shear product of the ith column with the shear inverse of the jth column. Okay, so W1 over 1 would be the all once vector, or more generally, Wi over I would be the all once vector. So this gives me a collection of n squared vectors, and we're going to be using them, dealing with them. Okay, and so I mean, if you're dealing with the Hadamard matrix, the shear inverse is itself, and so you're just taking the shear products of columns. That's the Hadamard matrix. But there are n squared, so you're getting a sequence. It's best to think that you've got a sequence of vectors indexed by I and J. Okay, but don't just think of them as set. So the identity is in there and it's in there n times, but it'll be all one vector is in there n times. So we just live with that. Now okay, so that's all right. I mean, that's not too bad an operation. We're using shear products. We're using shear inverse. Why not take shear ratios of 2 columns or 2 rows? The next step was in strategy. We're going to define the Nomura algebra. So this is going to be an algebra of matrices associated to the type 2 matrix. And it consists of the n by n matrices for which each of these vectors Wij is an eigenvector. Okay. Now, this is entirely arbitrary and wouldn't be the first or the second or the third thing you might think of, but it turns out to be important. We're going to see that this Nomura algebra is a commutative coherent algebra, for example. And we'll use that eventually to construct quantum permutations. Now, the minor comment here is that the Nomura algebra for the shear inverse of W is equal to the Nomura algebra of W. That follows from definition. If W is a type 2 matrix, so is W transpose, but the Nomura algebra of W and the Nomura algebra of W transpose are closely related, but they're not in general equal. And so we're getting pairs of algebras, but we'll come back to that. So now I've been throwing the word algebra around. The point is, if I have 2 matrices M and N, and each of these guys is an eigenvector for both M and N, then there are also eigenvectors for the product M times N. Okay, so that tells me that I do indeed have an algebra of matrices, and the identity is clearly in there. So that I have an algebra of matrices which have the matrices which have these guys as eigenvectors. So this is again, I mean, this is all designed to make the undergraduate student's life easier. The eigenvectors are given to you. You don't have to search for them. Yet another definition. So we have this. Well, it's often useful to think that we have an n by. Often useful to think of an n by n array of eigenvectors. So we have eigenvectors. What was I calling them? Wi over J. So I can put those into an n by n matrix, okay, in the natural fashion. And so it's often useful to think of that. Now, I don't want to put the vectors in there. What I want to put in there is the eigenvalues. So if you give me a matrix M that's in the Nomura algebra, then for each vector Y I over J, I get an eigenvalue. So now I can write down an n by n matrix of eigenvalues. So there are n squared entries. Now, M is an n by n matrix, so there's going to be a lot of repetition. It can only have n different eigenvalues. Okay, but still it's an array, and so and that's useful. And so we're going to call that the map that takes the matrix to its matrix of eigenvalues. We're going to call that theta. There it is, uppercase theta. Okay, and this is essentially the definition that is not essentially about it. Now, I like to say in mathematics, when someone says something is essentially this, it essentially usually means not. But this is the definition in symbols. So we're saying we know this is an eigenvector for M by definition, and so there's an eigenvalue, and we're calling it this. And since we've got n by n of them, we're going to stuff them in a matrix, which we call theta of M. Okay. Now, I said that the Nomura algebra contains the identity. Now, for all we know, it may be we pick our type 2 matrix and compute the numeral algebra and discover it is just the identity. Now, we can do better than that in the cases we care about. So the lemma I want to discuss, I think I'm going to leave for you guys. Suppose I got an invertible and Schur invertible matrix. So it's, then W is type 2. Okay, so this is just saying that the entries are non-zero. Sorry, this is saying the entries are non-zero, and this is just invertible as we're used to. So under those conditions, W is type 2, if and only if the all ones matrix is in the numeral algebra. Yeah, and I'll list this because this is a nice exercise. It's not especially difficult, and it's worth thinking about. So the we have a second characterization. Once we have the numeral algebra in hand, we have a second characterization of type 2 matrices. We have the definition, or now we could equally well say that J lies in the numeral algebra. Now, and so it follows that if W is type 2, the numeral algebra always contains both I and the all ones matrix J. And so when we're dealing with type 2 matrices as we are, the numeral algebra will always have dimension at least 2. The problem is we would like to have we really, really want examples where the dimension is greater than 2, and they're not easy to come by. Okay. I mean, if you can't, for various reasons. So in most cases, you pick your type 2 matrix and you laboriously compute the numeral algebra and you discover it's just the algebra generated by I and J. And in that case, the numeral algebra is not really going to help you anymore. Okay, but still, there are enough interesting cases that we persevere. So I wanted to give a relevant example, and so I'm going to take a primitive nth root of unity, and I'm going to use V sub n to denote the n by n van der Waals matrix. So there's the definition. Andries Brouwer assures me that van der Waals never wrote down the van der Waals matrix, but I forgot to ask him who did first. But when he makes comments about history, I always take them as correct. So this is just the standard van der Waals matrix. So the entries are powers of theta, and I've got to put in a -1s to get, I want to get it runs in first row and first column. So we do that. So we get this matrix. Okay. Now, for those whom it helps, this matrix is the character table for the cyclic group of order n. Okay, but I'm not going to say anything more about that. But the point then is that the Schur inverse of V is the complex conjugate, and the transpose of the Schur inverse is just the usual conjugate transpose. So that's a van der Waals matrix. And you can check that B times Bn star is equal to n times I. And so 1 over n times, what am I doing? 1 over n root n times Vn, that's a flat unitary matrix. Okay. So this is and so now the point is you can construct a lot of these things now because you can take chronic products, and what happens then is for each abelian group you can write down a type 2 matrix which is a flat unitary. But we won't be going into that. What I'm trying to work out here is what is the numeral algebra of this matrix. I'm claiming it's flat unitary, so it's type 2. What is this numeral algebra? And the claim is if you do the obvious calculations, it's the algebra of n by n circular matrices. Okay, so this is rather nice. You've got a really straightforward matrix, the van der Waals matrix. Okay, it's flat and unitary. It's the numeral algebra is the algebra of circulants. And that's certainly an interesting object and turns up in lots of places. Okay, so although this is our first example, there's some meat in it. The question, well, I was talking about type 1 and type 2. The question is whether the question is whether if you have a type 2 matrix which actually lies in this numeral algebra, then you have a type 3 matrix. Now I'm leaving out some weasel words there, but still that's good enough to go on with. So that the point I'm mentioning that in this case, note that the van der Waals matrix is not a circulant. Okay, well, we can sort of solve that. This is meant to be an eta that eta be a primitive 2nth root of unity. Now that's the 2nth root, not an nth root. Okay, and now I'm going to find a matrix W with ij entry equal to the theta to the I minus j squared. Okay, we'll call it force of habit to use. I didn't want to use theta again because theta was an nth root of unity. This is 2nth root of unity. Now this is a symmetric matrix with constant diagonal. Okay, and you can, the trick is that eta to the I minus j squared is eta to the I squared minus, actually for it, what is it? Eta to the 2ij, eta to the j squared, and you probably want a minus in this. Now, so what that's saying is that if this in the middle there is a van der Waals matrix using eta squared as your generating element. And these are diagonal matrices and invertible and unitary because the entries are to unity. So what that's telling me is that this van der Waals matrix is equivalent to this. Okay, so these are equivalent type 2 matrices. And this is a circulant. Okay. And so that's the precise statement is here. Something equivalent to W lies in the mirror algebra, then it's a type 3 matrix. And then type 3 matrices give you link invariants for links and knots. So since I've just been discussing examples, I want to go on a bit more of the theory. I said that the mirror algebra is a matrix algebra, contains I and J, if we're starting from type 2 matrix. The next thing I want to do is to prove it's commutative. Now, in a sense, the principle is obvious. I've got n squared eigenvectors. Surely I can diagonalize everything inside. And diagonal matrices commute. Now, in a sense, he's got to fill in the dots that are left there, but I'll go through a bit. So, since W is invertible, its columns are linear dependent. Okay, and if D1 is the diagonal matrix corresponding to, if entries corresponding to the first column of W, then it's invertible. Okay, and so the vectors D1 inverse times jth comma W, which I could also notice that should be a 1 there. Let's actually make that right too. Yeah, so these vectors are linear. So these guys are linear independent, and we've got a set of linear independent vectors. We're multiplying each of them by an invertible matrix, so these are linear independent. Okay, so now we have a linear independent set of eigenvectors for anything in the Nomura algebra, because these are the Nomura algebra is a set of things that has the W I over J as eigenvectors, and so everything in the Nomura algebra will have these n vectors as eigenvectors, and so therefore you can simultaneously diagonalize them. Okay. So it's basically the point is you're given too much. You're given n squared vectors. In fact, you're sitting in an array, and you only need the vectors corresponding to the first row, or the second row, or the third column. Anything works. Okay. So the algebra is commutative. Okay. Now there's two things you want from an algebra. It's nice if it's commutative. The other thing you want is to be close under transposes or conjugate transposes, depending on whether you have the reals or not. And so, but anyway, being commutative is half the battle. Now, one consequence that since the algebra is commutative, we get an important relation, namely that the matrix of eigenvalues, if you like, of m times n is just the shear product of the two matrices. Okay, so this map theta is taking the matrix product to the shear product. Those who might help, this means we're going to see that theta is an example of a duality map. But we won't go on with it. We're not going on anywhere with that. What's that doing? Okay, so you can also get that theta I is just the ones. Well, the eigenvalues of I are all 1. So theta I is equal to j, and theta of j is an n times I. And as I've said in many equations, with these sorts of equations, there's often an n floating around, and you can never remember which side to put it on. But I'm pretty sure I've got it right this time. So we have a map takes NW to another matrix algebra written by n matrices, and the multiplication on the original algebra NW corresponds to surmultiplication on the second algebra. Now we're going to see that the the image of NW under theta is also closed under matrix multiplication, and then we're going to deduce that NW itself is closed under matrix multiplication. Any questions at this point? So to go further, I need some idempotents. And I was revising this stuff about half an hour ago, so no, probably maybe an hour ago. It may be scrappier than usual, but I think it's okay. So I'm starting with an n by n type 2 matrix, and I'm defining a family of matrices, y sub ij. Okay, and so it's not quite an outer product, but it's it's trying to. So anyway, so we've got these family matrices. So it's a rank 1 matrix. Okay, that is obvious. 2 things which I'm leaving as exercises is you can show that if you take, again, if you think of these as sitting in an n by n array, and we will be, then the entries in the same column, in the same row, are orthogonal, and it will follow from things we say later on that the entries in the same column are orthogonal, and that the sum of these things is the identity. Now these are idempotents, but they're not projections because I can't prove that there's closed in a conjugate transpose. And in general, and I can't prove that because in general it's not true. So we've got to be a little bit careful because we're so used to dealing with that. We're used to dealing with that quantum permutations, and we have these projections, and they're looking at, say, look like this guy. But the point is, we're not assuming that they're closed under conjugate transpose, and they may well not be. Okay, so you've got to be a little careful. On the other hand, it's interesting because we're getting matrices that we'll see some matrices that look a lot like quantum permutations, but differ only in that respect that the entries are still idempotents, but they're not necessarily projections. And it's interesting that there's those relaxations actually exist and have some use. And so what we're going to show is that that these guys, the guys in a given row, form a basis for the elements of the mirror algebra. Because despite appearances, this is just a scalar. This is just an eigenvalue of m. And so this is essentially a spectral decomposition of m. I say essentially because some of these values could be equal, and so it's technically a refinement of the spectral decomposition of m. You may split one of the idempotents as a sum of 2 things, and so you may get some repetition. But well, okay. So and so I've sketched the proof here. It's not sure it's really worth me going through. You just yeah, I think I just leave it as it is. It's there. Yeah, so you can check through that, and so we get that we have this relation. Now, so we can write the entries in any row span in the mirror algebra. Now, each row will give us a collection of things to span the mirror algebra. The columns will give you things which span the mirror algebra of the transpose of W. Now, the critical result, which I'm not going to prove at this point, is that well, another version of this, if M's in the Nomura algebra, then theta relative to W, which is the only one we're using up now, applied to this vector, is equal to scalar times that vector again. So in other words, the A over B, well, call it the A over B column of W transpose is an eigenvector for theta W M with eigenvalue MAB. Okay. Now, this implies a couple of things. First thing, it implies that theta of M itself is in the Nomura algebra of W transpose. You can also see at this point why I don't want to say that W and W transpose are equivalent, because they're really behaving differently in this setting. Okay. If you take two equivalent Hadamard matrices, the Nomura algebra doesn't change in any sensible fashion, in any fashion that you care about. Okay, but the transpose does have a role. Okay, so the first thing this tells you is that, well, theta, that should be it. I'll put it in. So theta W is mapping M into NW transpose. And if you work through it, you discover that theta W transpose applied to theta of M is equal to N times M transpose. So that tells you a number of things. First thing, it tells you that these two mappings are invertible because their compositions, their identity. It also tells you that M transpose is in the Nomura algebra of W. And remember, I said before, when you're having the algebra commutative is nice, but you also want it to be closed on a transpose, and you get that. Now, the surprise is it's a little bit hard to prove. You know, these calculations just take a line or two. There's nothing, you know, once it occurs to you that you want this, you can get the calculation. But the one consequence, or there are two important consequences, two or three. So theta W is mapping M into the Nomura algebra W transpose, but the product of those two things is a scalar times the transpose map. And so, and thirdly, the transpose of an element of NW is in MW. This theory was all worked out by Nomura, which is one reason they're called Nomura algebras, although he may not, these aren't his proofs. Okay, so what's the time? Okay, so go on a little bit. So I've got these idempotents, and I've got some interesting properties. And so the next thing I want to work with is the, well, as I've alluded to it already, the n by n matrix whose ij entry is yi over j. So it's an n by n matrix. The entries are idempotents. Each row sums to the identity. Each column sums to identity, because to get the columns, you just work W transpose. Okay, so you have a matrix of idempotents. If those idempotents were projections, it would be a quantum permutation, but they don't have to be. Okay, so I need to define the matrix. So the we're starting with the n by n type 2 matrix, and we're defining W to be this. Okay, so this is, you know, as we said before, it's effectively an outer product, if you don't mind swapping things around a bit. So it's a rank 1 matrix, it's a block matrix, and the y sub I is just 1 n times the identity. Okay, so we have I have an n by n matrix of idempotents, and since we've been working with quantum permutations, that sort of situation shouldn't cause any problems. So I'm going to call the matrix that I get in this fashion script y sub w, and I call it the matrix of idempotents. Let's actually do that. W. Now, this is not a standard object in the theory of type 2 matrices. It probably doesn't exist outside my notes, but anyway, that's what we're calling it. So there are a few special properties you can notice, and so there are things you could verify, but I'm not going to leave it to you. First thing is that the transpose of an entry is the ij entry is just the ji entry. And so I'm writing, so y transpose is equal to y. Now I'm cheating a bit there. If I've got a block matrix, I'm taking the transpose. What I'm actually doing is applying in this case, what I really mean is the partial transpose. So I'm taking the transpose of each block. Okay. And so maybe I should use a different, actually I was using a different term, and so I'll continue to do that. So we're taking the transpose of each block. So we have a circle and a minus for Schur inverse. And so, okay. And we can also check that if you take the Schur inverse of each block, okay, then the resulting matrix is n squared times the transpose. So, and finally, you can get the transpose as 1 on n times the Schur inverse. So there are properties there which fall out. None of these are difficult. Now, I think I can get into my preparation. Yeah. So this is I'm going to be a bit early, but so if Y is the matrix of idempotence of an n by n type 2 matrix, each row and column sums to the identity. Okay, and again, that's just a straight calculation from the definition. Okay, and I didn't think I was going to get this far today. So the okay, I'll leave the proof for a minute. The connection to what we're concerned with comes up now. If W is a type 2 matrix, then the matrix of its matrix of idempotence is also a type 2 matrix. Okay, and if W is flat, then it's a flat type 2 matrix. And so it's a quantum permutation. Okay, and so the end result of this is if you have a flat unitary matrix, a Hadamard matrix or something coming from uniform mixing, or just some flat unitary matrix that you care about, and associated to that, there is a larger type 2 matrix, which forms a quantum permutation. Okay, and so to make it briefly, so flat unitary matrices give rise to quantum permutations. Okay, and type 2 matrices give rise to type 2 matrices of bigger size. Now, there's no suggestion you can get all quantum permutations in this way, because you're getting an n squared by n matrix with blocks of size n, so there's restrictions on the sizes. Okay, but on the other hand, and the point is, it's fairly easy to write these down. If you're given the unitary, you can write down the Yij's. Okay, and so you can construct the matrix. Okay, and the theorem is that matrix will be a flat unitary in this case, and in addition, be a quantum permutation. Now, there's been a fair bit of work on type 2 matrices, but it's comparatively new observation that you can get from flat unitaries to quantum permutations. Although there are constructions in the literature which would overlap some of this. Now, did I go any further? No. What did I want to say? So I went as I said, I can also get information about the Nomura algebra by working with these matrix of idempotence, and although I've got some time now, I'm not going to go into it today. So I can write down the result though. That might be useful. So let me start a new page so that they call a theorem. NW. Oops, I do it every time. And so the mirror algebra is arising as a set of things that commute with the this particular quantum permutation. Okay, and so this is again connecting the two subjects. And in fact, it's with the dual to this, or whatever you want to call it. And so we have a description of the mirror algebra and a description of the mirror algebra of the transpose, and it's kind of interesting in that we're working with our quantum automorphisms. We're looking at actually we're looking at when this guy commutes. So this is saying this would be saying that YW is a quantum automorphism of things in N. Okay, so actually, yeah, we haven't. There's probably some meat there. So that anything in the mirror algebra W transpose, any graph in there, has a quantum automorphism, which is the YW. And I don't, yeah, so, and so if the entries of YW don't commute, then you've got yourself a non-commuting quantum automorphism. Now, in thinking about quantum automorphisms, we didn't consider what happens if you reverse the order of multiplication. This comes up because this is n squared by n squared, so you have the option of playing with this as well. Okay, but I don't really understand exactly how this works. But both of these things, proving one of these things is as easy as proving the other. There's no difficulty with the proofs. The question is, what does it mean? And the other question, which we should be thinking about, is what interesting examples of quantum automorphisms if any, does this produce? I mean, at the moment, for all I know, it could just produce only classical things. But I don't know if I believe that. The other problem, the real problem is going to be that most of the time, N of W is just linear combinations of I and J. But there are other examples. There's Schmidt proved that the Higman-Sims graph has quantum automorphisms that are not commutative. And so there's probably a connection to this. But I'll stop there for today. Questions?